This is the video that covers Chapter 3.2 and 3.3 of the Precalculus course. Our objectives today is to discuss the logarithmic function and how do I convert from the logarithmic function to the exponential function. After that, we're going to go through various properties of logarithms, including the domain and graph and the common and natural logarithm. Okay. First off, just to remind ourselves, okay, the exponential functions are functions of the form b to the x, where b is greater than 0 and b cannot equal 1. Okay, so examples of exponential functions are below, where 2 to the x or 0.1 to the 2x. Okay, these are all situations where the x is in the exponent portion, okay, not the base. B is considered the base of the function. In the logarithm, okay, the logarithm is the inverse function. Okay, remember that the exponential function passed the horizontal line test, which means it has an inverse, and the logarithm is going to be that inverse. So when I do f inverse of f, I get x back, or if I do f of f inverse of x, I get x back as well. Okay, so the base of the logarithm, so if I have the exponential function b to the y equals x, okay, that b now becomes the base of the logarithm. So I can rewrite b to the y equals x as y is equal to log base b of x. Again, b is called the base of the logarithm, and this is generally pronounced as logarithm base b. Okay, and just like in the exponential, b has to be greater than 0 and b cannot equal 1. Okay, so converting between the exponent and logarithm, we use the definition of the logarithm. Okay, so here are 4 examples. Okay, log base b of x equals c. So we take b to the c equals x, and we do that for all of these situations. Remember though that exponents of a half, in the third one we have log base 3 of x equals to 1/2. So in this case it becomes x is equal to 3 to the 1/2, or basically square root of 3. Okay? So these are just ways I can convert between the logarithmic form and the exponential form. Okay, in chapter 3.4, we'll look at a different way of doing this that may perhaps make a little bit more sense. So, evaluating the logarithm. What the point of the logarithm is to basically give you the exponent. A lot of times, we're more interested in the exponent than we are in the number itself. Okay, so if I have y is equal to log base 10 of 100, we're basically asking what exponent is 100 if I started with a base of 10? Well, 10 squared is 100, so log base 10 of 100 simply becomes 2. Okay, continuing down in the second example, okay, log base 5 of 125 becomes, well, 1 over 125, sorry. 1 over 125 is actually 5 cubed on the bottom, or 5 to the minus 3. So the result of this is y is equal to minus 3. Or in the third case, the answer is 1/7. Okay, so we're very interested in the exponent, and so that's all we're going to really focus on when we're asking for the logarithm. Okay? Couple of properties of logarithms. Okay? The first property and the second property are very closely related. Okay? The first one is the 0 property that says log base anything of 1 is going to equal 0. Okay? Because anything to the 0 equals 1. Okay, so it doesn't matter what b is as long as b is positive and not equal to 0. The second property is the 1 property. Okay, log base b of b is equal to 1, again, because b to the 1 equals b. Okay, so that's the 0 and the 1 property. The inverse property we'll see more of in 3.4, but this is an incredibly useful property because this is how we will get rid of logs and exponents. Okay. In the first case, if I have log base b of b to the x, I get x. And if I have b to the log base b of x, I also get x. And we'll see in chapter 3.4 how this lets us get rid of the exponent or get rid of the logarithm. Okay. The next property is the exponent property, and this one is very useful. okay? Because this is really what the logarithm is almost all about, okay? And that's where I have log base b of a to the n. B and a don't have to be the same number, okay? But log base b of a to the n is going to equal n log base b of a. So I basically take the exponent down and put it in front as a coefficient, okay? And that will be very useful as we go forward. Okay, looking at the graph of the logarithm at the exponential function, okay, the blue line here is a graph of 3 to the x, an exponential function. It has a horizontal asymptote at y equals 0 and a range of 0 to plus infinity. Okay, when we take the inverse, one way to do that is to just reflect it over that line y equals x. Okay, when we do that, we end up with the red graph, and that red graph is log base 3 of x. So in this case, we can see that it has an x-intercept of 1, and again, y equals 1 when x is equal to 3. Okay, and the logarithm function has a vertical asymptote at x equals 0, okay, and a range of minus infinity to plus infinity. When we take inverses, the domain and range switch, and horizontal and vertical end up switching. That's what happens when we switch y and x in our graph. So, looking more specifically at the domain and the range of the logarithm, the domain of any logarithm is going to be 0 to infinity. The range of the exponential function is 0 to infinity. The range of any logarithm is minus infinity to plus infinity, okay, whereas that happens to be the domain of your exponential function. All logarithms will have an x-intercept at the x equals 1, and if b is greater than 1, the graph will increase to the right. As shown in the previous graph, it increases to the right here. If b happens to be between 0 and 1, the graph decreases to the right, and that's what we have shown here in the graph in the corner. Okay, so for example, okay, find the domain of log base 5 of x minus 5. Since we're talking about x minus 5, what we've basically done is we've translated my original graph of log base 5 of x 5 units to the right, okay, because it's x minus 5 in parentheses. Okay, so we're just moving it to the right or to the left, in this case 5 units to the right. If it was just log base 5 of x and then minus 5 outside of the parentheses, we're basically translating it vertically by 5 units. Okay, but in this case we're translating it to the right 5 units. So at that point, my y asymptote, my vertical asymptote, becomes x equals 5, or solving for it, okay, the domain of my logarithm must be greater than 0. Okay, in this case, what we're talking about is x minus 5, so x minus 5 must be greater than 0, and solving that, we end up with x greater than 5, and the domain is 5, comma, infinity. Okay? So, this is the same thing as a graph example. You can see how the vertical asymptote and the whole graph has been translated 5 units to the right. Okay. Couple of common versions of logarithms we'll see. The most common logarithm that we'll probably see is base 10. Okay. And base 10 is so common that we'll usually ignore the 10 and not even write it. Okay. So if we just see log x, okay, that log is assumed to be 10. So using some of the properties of the log base 10, we see log base 10 of 10 equals 1, and log base 10 of 1 equals 0, and the inverse is below. Log base 10 of 0 is undefined. It's undefined for everything because the 0 is outside of my domain. It has to be greater than 0. The second most common logarithm we'll see is the natural log. The natural log is actually abbreviated ln. Okay, we have those two buttons on our calculator, log and ln. They're on the left usually, and right next to each other. Okay, the log on your calculator doesn't have a base, it's log base 10. Okay, there is a way on your calculator using the libraries to get a log of a different base, but we'll see a different way of calculating that. Okay, so in this case, e becomes the base, the natural number that we talked about in 3.1, and the logarithm is abbreviated ln, and again we see the properties of the natural logarithm. Okay, a few more properties of logarithms, and these properties apply to all bases. Okay, we've already talked about the exponent or power rule. The next rule is the product rule, and this is very useful for expanding or compressing logarithms. Okay, and that's where log of a times b is going to equal the log of a plus the log of b. Okay, do not make the mistake of saying, well, the log of a times b is going to equal log of a plus log of b. The quotient rule is very similar to that, in that log of a divided by log of a divided by b quantity is going to equal log of a minus log of b. This rule pretty much follows from the product and the exponent rule, because log of a divided by b is the same as log of a times b minus 1. Using the exponent rule, b minus 1 becomes minus 1 log b, and the product rule gives us log of a plus minus 1 log b, or effectively the same thing of log a minus log b. Okay? And we can use these rules to expand logarithmic expressions. So if I have something very complicated looking like log base b, x to the 4th cubed root of y, okay, I can break these things into little smaller sections. Okay, first I convert the cubed root to the 1/3, an exponent of 1/3. Then I use the product rule to split off the x's and the y's. They both keep a log of the same base b. Next I apply the power rule to take the exponent down for both logs, and I end up with the form shown there. Okay, doing this in reverse, okay, means I can sometimes solve questions that I wouldn't have been able to solve. So in this case, log of 25 plus log of 4. Notice there's no base given, so this is going to be the common log, or log base 10. As long as they're the same base, I can combine them back together, because 25 plus log 4 is the same as log 25 times 4, or basically log of 100. Well, log base 10 of 100 is really just 2. In the second case, we use the quotient rule, and we end up with log of 7x plus 6 divided by x. Okay. The third one's more complicated, but again, it's just a matter of applying the various logarithm expressions in order until we end up with the final result. Okay? Thank you very much. Oh, the last property, keep forgetting this one. Okay? The last property is how I can change the base of a logarithm. To change the base of a logarithm, divide the original logarithm by the logarithm of the new base. Okay? The two logs have to have the same original base. So if I start with log base a of x, and I wanted to convert it to log base b of x, I can do that by dividing by log base a of b. Okay, and that will give me log base b of x. And so using your calculator, you could convert the natural log or the common log into a log of a different base simply by dividing by that new base. Okay, the log of that new base. Okay, thank you very much.